Remember in our previous video that we looked at the decomposition of ammonium carbamate, and we produced all gaseous products. And the same is true, of course, for combustion reactions. Now, since we can't easily separate most gases from each other, most of the time, if we're talking about a reaction like that, we have a mixture of gases as our products. And if we're collecting gases, then we're going to have a mixture of gases in whatever our collection container is. Now, the great news is that because we're considering ideal gases only, all of the gas pressures add up together to give us our total pressure. This is called Dalton's law of partial pressures, or just Dalton's law. So first we need to know what a partial pressure is. So let's think about a container. Let's say we have two gases in there, and I'm going to represent one of them with these little X's. And so the pressure of gas X is P sub X. This is the partial pressure of gas X. And then I'm going to represent my other gas by little dots, or O's. So all of the little gas particles for this little gas O, they add up to a certain amount of pressure. And so each one of these has a certain amount of particles that are hitting the wall. We remember that pressure is defined as the force of the particles over the area. So we have a certain amount of area that is the container here. And then each of these particles will hit the walls with a certain amount of force depending on how many particles you have. And so this will give us our partial pressure, and our total pressure is going to just be the sum of these partial pressures. And although I have two gases in my example, it really doesn't matter how many gases you have, because your total pressure is just the sum of however many gases there are in your system. So you can have as many as you want, and they just will all add up together. And this works because our gases are ideal, and so they don't really interact in any significant way. So if we're talking about the ideal gas law, the other way to think about this is that the moles of each of our gas particles are going to add up together, right? If I have the partial pressure of gas X, that means, that my gas X is in a container with volume V, and it has the number of particles. It has N sub X moles, and the gas constant is constant. It has whatever temperature is in my system. And my other gas has the same kind of deal. The things that are different about it are the moles and the pressure. So the moles and the pressure correlate with each other. So my total number of moles is the number of moles of each gas added up, right? And if I think about the ideal gas law in this context, then I could solve for the number of moles from the ideal gas law, and it would be P sub X V over RT, P sub OV over RT, and the number of moles would be P total V over RT, right? And so we can see that these RTs are all the same and these V's are all the same, and so this just reduces to give us Dalton's law. So one of the ways that we also can think about this is instead of going directly to all pressures, we can hang out for a second here, and we can say that our pressure, our total pressure here, V over RT, is going to be related to the number of moles of each of our gases, right? And So the sum of the number of moles of our gases is related to our total pressure. And one of the ways that we talk about these instead is to say that the amount of each of our gases is contributing to the total pressure in a way that's relative to the number of moles, right? If I have a 50-50 split here, where half of the mole particles are gas X and half of them are gas O, then that means that my partial pressure for the X is going to be half of the total pressure, and the partial pressure for gas O is also half of the total pressure, right? That depending on how much of each of our gases we have, that's going to determine what fraction of the total pressure it is made up of each of our individual gases. So the way that we do this in general is we define mole fraction. The mole fraction, when we use capital X for this, if we were talking about the mole fraction of, I'm going to use A now, of gas A, that would be the number of moles of gas A divided by the total number of moles of any gases in the system. So let's do an example problem and actually see how this works. So here's our system. We have a gaseous system I need a pressure at 3.29 bar. This is a total pressure. Contains 0.391 moles of ideal nitrogen gas, 0.426 moles of ideal argon gas, and 0.604 moles of ideal helium gas. And so we're going to ask, what is the partial pressure of each of the gases? Now we can't do this directly, right? Because we can't just use the ideal gas law because we don't know what the volume or the temperature is. So we need to use the relationship of the mole fractions. So first we're going to calculate the mole fractions, and then we're going to realize, so here's our mole fraction again. That the partial pressure of each gas is equal to the mole fraction times the total pressure. So let's look at how this works. Our mole fraction of nitrogen would be, what's our total number of moles? Our total number of moles is the moles of the nitrogen plus the moles of the argon plus the moles of the helium. So I get 1.421 moles. So our mole fraction is going to be the number of moles of each gas divided by the total. So my nitrogen, I have 0.391 moles, and I'm going to divide that by 1.421 moles. And my units will cancel out here, and I will get a fraction of 0.275. So if you want to think about percentages instead, that means that 27.5% of all of the gas particles in the system are nitrogen gas, if you just want to connect to something else. So go ahead and calculate the mole fractions for the argon and the helium. Pause the video and put in your numbers. All right, hopefully, since we have 0.426 moles of argon. You got 0.300. Please make sure to keep 3 significant digits for the argon. And for the helium, I got 0.425. So one of the first things to be aware of is that because these are fractions, they need to all add up to 1. So however many gases you have, if you add up those mole fractions, they all need to add up to 1. So check that and make sure that it adds up to 1. So now when we calculate our partial pressures, we know that 27.5% of the gas particles are nitrogen. So that means that 27.5% of the total pressure, which was 3.29 bar, is going to be from the nitrogen gas. So I get 0.905 bar from that. And so the partial pressure of the argon and the partial pressure of the helium you can calculate the same way. So go ahead and pause the video and try that out. Hopefully you got 0.987 bar and 1.40 bar. And the other thing that's true for a check, like this was a check that we could do, the other check that we can do here is that we know that the partial pressures all have to add up to the total pressure. I actually made a mistake when I was doing my work for this video the first time, and I accidentally used the, what did I use? I used the number of moles of the helium instead of the mole fraction of the helium. I just, copied the number down wrong. And so when I added them up, I got a number that was bigger than my total pressure. And I went, wait, what? What happened here? So if we add up all these pressures, then they also have to add up to our total pressure, 3.29 bar. And so double check and make sure that these do. And this is another really good check, just to make sure you haven't made a clerical error here. So dealing with partial pressures and mole fractions should be relatively straightforward. And you can check your math to make sure that it works. So the other thing that I want to talk about in this video is the last piece that we're going to do out of Chapter 5, which is that when we think about gas behavior, we started this chapter by talking about the historical view of gases, that we didn't have a particulate view. But we do have a modern understanding of what it means for gases to be a gas and that they are particles. And so we have a more expanded theory that we're going to briefly talk about called kinetic molecular theory that helps us understand why these gas laws work the way they do. And so if you've been having a hard time kind of getting your head around why when we increase the pressure, the volume decreases, I think this will help a lot. So kinetic molecular theory, all we're really doing with this theory is helping us understand the gas particles. Our chapter does go into some calculations. We're not going to worry about those ones. So this really is plus some ideal gas law concepts as well. So some ideal gas law concepts are inside this kinetic molecular theory. So our principles for the kinetic molecular theory is that gas particles are going to act like tiny little balls. And just like the ideal gas law, we're going to say that they have mass, but no significant volume. So they don't take up any of the space of our container. And also, like what we've already talked about, we're going to see that our gas particles move in straight lines, and they're really in straight random paths. So, they don't just follow one path. They bounce off and have random paths throughout our container. And they're constantly doing this. They're constantly in motion. So this part is new. Our average kinetic energy, and remember that kinetic energy is energy of movement, and it's routinely described as 1/2 mv squared, where m is the mass of the particle and v is the velocity. I haven't written this as a vector because we're not really worried about vectors in this particular class. If you do this in physics class, then you will see that v has a direction as well as a size, and that this becomes important. We're just talking about it in terms of a qualitative understanding. So our average kinetic energy, how fast our particles are moving, this is going to be related to the temperature of the gas. And so I think it shouldn't surprise you that if we have a higher temperature, we have a higher kinetic energy and therefore faster particles. So here's another part that we've already talked about from the ideal gas theory, which is that our gas particles are always going to undergo elastic collisions. And so since those collisions are elastic, they aren't going to affect the temperature or the kinetic energy. And that the other corollary of these gas particles undergoing elastic collisions is that they don't interact with each other except through these elastic collisions. So they don't experience attractions or repulsions. So now that we're kind of thinking about gases as particles, we can explain the different gas laws. So we're just going to kind of quickly review. We had Boyle's law, which said that pressure was inversely related to volume. We had Charles' law, which was that volume is proportional to temperature. We're going to have Avogadro's law, which was that volume was proportional to the number of moles. And then Amundsen's law, which is that pressure is proportional to temperature. So if we think about Boyle's law says that if we squeeze our particles together and give them less space, the pressure goes up. Actually, we've got a good visual. Let me grab it. Okay, this is one of our figures from the book. And here's our initial state over here on the left, that we have a certain amount of pressure, here's the gauge, we have a certain amount of volume, and we have a certain number of particles. So we're going to skip over this middle one here and skip over to the right-hand side. So we've given our particles more space. We have increased our volume, but kept our number of particles the same. So in this case, now our pressure decreases because our particles have a further distance to go before they hit one of the boundaries. And so they're having fewer collisions with our outer area, which means less force. So if we go back to our idea here, that as we increase the volume, the greater space means fewer collisions with the surroundings. Pressure is equal to force over area. So, and we also have a larger area. So pressure is going to go down. And the same thing is true if we do the opposite. If we decrease the amount of space that our particles have, we squeeze them together. So they have a smaller space to bump around in. They're going to hit the walls more often. And so the pressure is going to naturally be a little higher. So that's our Boyle's law explanation. Our Charles law relates to our kinetic energy. If we increase the temperature, that means our kinetic energy increases. So the particles are moving faster. And in Charles' law, we have to keep the pressure the same. So if we want the pressure to stay the same, the particles need more space to move around in. Otherwise, the pressure is going to increase because of those increased collisions with the surroundings, with the wall. So we have to increase volume. And the same thing is true if we decrease the temperature. If we cool those particles down, we're going to slow those particles down. And so if our pressure needs to stay constant, we have to give it fewer spaces so that the force of those particles, the number of collisions against the wall, stays consistent with the decrease in the speed. All right, Avogadro's law has to do with the number of particles. It should make pretty good sense that if we increase the number of moles, if we put in more particles, and we want to keep pressure and temperature constant, they need more space in order to keep the pressure and the temperature constant. And the reverse would be true. If we take out the particles, then we're going to decrease the amount of space for that system. Okay, the last of our 4 simple laws here was Amundsen's. And this is about temperature and volume. So if we are increasing the temperature, but we keep the volume constant, then so we aren't increasing the size, but we increase the temperature, the kinetic energy of the particles increases, so their speed increases, their speed and velocity increases, and so that means more particles are going to be hitting the container. We have the same amount of area, so our pressure is going to go up. This is why they have a direct relationship. Okay, so this has gone through the amount of stuff we're going to actually do with our kinetic molecular theory. We're just going to have this qualitative understanding. And although our book goes through calculating average speed of our particles and talking about diffusion, we're not going to talk about those. We're also not going to talk about real gases in this class. You can have that in physical chemistry for later.